Problem 1. Refrigerator. A water cooler for drinking water should cool 25 liters per hour from 18 to 10 degrees Celsius while the water reservoir gains 60 watts from heat transfer. Assume that a small refrigeration unit with a coefficient of performance of 2.5 does the cooling. Find the total rate of cooling required and the power input to the unit. We are given a volume flow rate that enters the cooler at hot temperature of 18 degrees Celsius and leaves at a cold temperature of 10 degrees Celsius. The reservoir gains heat of 60 watts. The coefficient of performance of the refrigerator is 2.5. The required values are the flow work rate and the rate of heat loss. The law of conservation of mass of this process is mass 1 is equal to mass 2. To simplify, let mass 1 and mass 2 be equal to mass. The first law of thermodynamics of this process is the rate of change in enthalpy equal to the sum of rate of heat transfer and the rate of the work. For ideal gas, enthalpy is Cp dt. Hence, the equation mass flow rate is equal to the volumetric flow rate multiplied by the density of the substance, for which in the problem, it is water. The mass flow rate is equal to 6.92 times 10 raised to the third power kilogram per second. At the rate of heat loss, we will adjust the values in the given equation, resulting to the rate of heat loss equal to minus 171.4 kJ per second or minus 171.4 watts. For the flow work rate, we will use the equation of coefficient of performance, denoted by beta, equal to the rate of heat loss over the flow work rate. Hence, flow work rate is equal to heat loss over the coefficient of performance, resulting to minus 68.56 watts. Problem 2. The exit nozzle in a jet engine receives air at 1200 Kelvin, 150 kPa with negligible kinetic energy. The exit pressure is 80 kPa and the process is reversible and adiabatic. Use constant heat capacity at 300 Kelvin to find the exit velocity. At state 1, we are given with 1200 Kelvin and 150 kPa of air. At state 2, the exit pressure is 80 kPa. We are required to find the exit velocity of the system. For the law of conservation of mass, mass at state 1 is equal to the mass at state 2. Applying the principle of first law of thermodynamics, change in enthalpy plus change in kinetic energy is equal to the heat transfer and work done. Since the kinetic energy at state 1 is negligible, and the process is reversible and adiabatic, and change in enthalpy is equal to Cp dt, the resulting equation is exit velocity is equal to the square root of 2 multiplied by the specific heat at constant pressure times the change in temperature. For the second law of thermodynamics, since it is reversible, heat loss is 0. Therefore, the entropy at state 1 is the same at state 2. From table A.5 of Sontag, we can get the values of the Cp and K. Since it is an isentropic process, it gives us this equation. Substituting the values, we can get the exit temperature. Applying the formula from the first law of thermodynamics a while ago, substituting the values, the exit velocity is equal to 629.4 meters per second. Problem 3. A condenser in a power plant receives 5 kg per second steam at 15 kPa, quality 90% and rejects the heat to cooling water with an average temperature of 17 degrees Celsius. Calculate the irreversibility for the condenser assuming an ambient temperature at 17 degrees Celsius. We are given a mass flow rate of 5 kg per second which enters at a pressure of 15 kPa and a quality of 90%. The ambient temperature in this process is 17 degrees Celsius. we are required to determine the irreversibility of this process. The law of conservation of mass is the mass in state 1 equal to the mass in state 2. The first law of thermodynamics is the mass flow rate multiplied by change in specific enthalpy equal to heat flow rate. Since we are calculating for the irreversibility for the condenser, the second law of thermodynamics is as shown. The specific enthalpy and specific entropy of each state are taken from table B.1.2 of Sontag. Since the phase of the entering mass is vapor, the specific enthalpy and entropy of the vapor are computed. The heat released is determined by substituting the values to the first law of thermodynamics equation. Substituting the computed values to the equation of irreversibility, the irreversibility is calculated to be 1208 kilowatts. After determining the heat, the entropy generated can now be computed.